All right, continuing on, following up on our spectral projectors material, some related material. Recall in section 3.2, we took an inner product of matrices, A and B. If A and B are matrices of the same size, say the columns of matrix A are the vectors A1 through A sub m, columns of vector B are the vectors B1 through B sub m, we define the inner product as the sum from j equals 1 to m of A sub j transpose times B sub j. That's just the inner product of the jth column of matrix A with the jth column of matrix B. Written in terms of the transposes, remember we're treating every vector by default as a column vector. So by transposing the A sub j vector, that gives us a row vector. So we have a row vector times a column vector in a matrix product sense. So indeed, that really is just a dot product of the columns. So what the inner product of two matrices really is the sum of the product of all corresponding parts. So multiply corresponding entries in matrix A with corresponding entries to matrix B and add the whole thing up. So inner product of matrices was defined as that. Now we've been looking at these outer products of vectors. So suppose we have V1 through V sub m, an orthonormal set of vectors, and we want to consider the outer product V sub I transpose. If these are vectors from Rn, then these outer products are n by n matrices. Remember that? The inner product is arguably a 1 by 1 matrix. That's why it's called a scalar product. But the outer product, we go in the other direction with a transpose, and we produce, say, n by n matrices. We want to talk about the jth column of that outer product. Okay. Think what'll happen. V sub I is a column vector. V sub I transpose is a row vector. So when we do the multiplication, we'll do a row of V sub I, so that'd just be a single entry from V sub I, times a column of V sub I transpose, and that'd just be a single entry as well. If you want to pick out the jth column of this matrix, then we'll need to look at what we get by going to the entry V sub I super j being the jth entry of V sub I, and then multiplying that by the entry V sub I and V sub I transpose. Usual way of taking a matrix product, except we're picking off an entire column here. So we get a scalar multiple of this column V sub I. All right, with that said, we've got the jth column of this matrix expressed in terms of a scalar and a vector. And be careful, the notation's not entirely clear. V sub I super j is the V sub I, the jth entry of V sub I as a vector. So this is a scalar, this is a scalar, and the V sub I is a vector. So we want to take an inner product, say, of this V sub I transpose, this outer product with itself. So that's an inner product of a matrix with a matrix. That's why we brought that up again. And to do so, we need to talk about the jth column of each of these matrices. We need this jth column of the outer product. So here's an expression for the jth column. Let's make that a little bit bigger. All right, so we need the transpose of the jth column. All right, so we take V sub I super j V sub I and transpose that. All right, that'll give us a V, so a little typo here, that should be V sub I. That gives us a V sub I super j V sub I transpose. And then we'll take the jth column of the second matrix, which is the V sub I super j V sub I. So as observed up here, that's how you calculate an inner product of two matrices. All right, remember the V sub I super j is a scalar. Same thing over here, v sub I super j is a scalar. So we can pull those scalars out to the side, properties of scalars, and we're left with a v sub I transpose times v sub I. Here we go, v sub I transpose times v sub I. Here's the scalar stuff pulled out of the vector product. Oh, and that's just an inner product. When we have the transpose first and no transpose, that's an inner product. We started with the transpose second in a product of this form. That was the outer product. But here we got an inner product out of this. So we get the sum, j equals 1 to n. We're summing the components of v sub I. That'll give us the norm squared of v sub I. We're summing the component squared, I should say. So that gives us the norm squared of v sub I. And this is an inner product of v sub I with itself. We said these vectors are orthonormal. Okay, so the inner product will be the norm squared, which we know to be 1, because v1 through v sub m, it's a collection of unit vectors. So we're getting an inner product of the outer product, v sub I transpose, to be 1. What if we take the inner product of the outer product, v sub I transpose, v sub k transpose? So we're looking at an inner product where some things are the same and where some things are different, as we've often done when we've looked at orthonormal things in the past, orthonormal sets of vectors in the past. We're ultimately looking at an orthonormal system of matrices here. Okay, same situation. We'll get the jth column of this first one. Okay, that requires a transpose. We'll get the jth column of this second one. Okay, we know how to express that. It's something of this form, except the index down here is k, not I, in that second one. I can still collect the scalars together as we did upstairs. We still get a inner product, this time of v sub I with v sub k, same thing that happened upstairs, except this time I and k being assumed to be different implies orthonormal system, that inner product will be 0. So what we see is these outer products are 1, inner product with themselves is 1. And when we take an inner product of one of these things with a different thing, one of these, it sounds weird, the inner product of these outer products, we get 0 when we use different indices. All right, if we define P sub I to be V sub I transpose, should read V sub I transpose, as we did above when we had the spectral projectors. Then we see that these matrices, thusly defined, is an orthonormal system of matrices. So up here we've shown the inner product of P sub I with itself is 1. The inner product of P sub I with P sub k, where I and k are different, is 0. Orthonormal system, except this time it's matrices instead of vectors. So if we have these spectral projectors as we had above, and in that case, these vectors came from being eigenvectors for a particular matrix, then we can write matrix A in terms of the spectral projectors, if in fact these are spectral projectors, or more generally in terms of these outer products. So what we get, knowing we have an orthonormal system, is a representation of a thing, in this case not a vector but a matrix, as a linear combination of coefficients times these things in that orthonormal system. These things are these outer products of this collection of orthonormal vectors. We stated something, I think, similar to this upstairs, where we had specifically the spectral projectors down here. All right, you think of inner products as projections. We're projecting A onto this vector and then taking the direction from this. Since we have an orthonormal system of matrices, we get this usual projection times vector summation, a Fourier expansion, these guys called it. That's the beauty of having an orthonormal basis for something or other. And that's exactly what we've got. The spectral projection was also written in this form, provided we had these vectors v sub I and v sub I transpose as eigenvectors of matrix A. So when we had the spectral projection, then we must have equality between these two because we're using the same basis, this collection of n outer products to produce those matrices. And so the coefficients up here must be the same as the coefficients down here. The C sub i's coefficients, C sub I for coefficient, also was eigenvalues when we had the spectral decomposition. But we get that those C sub I values must equal these inner products as given here. You know we've got a unique representation, unique representations with respect to bases. So here we've got two here and here we've got two representations with respect to the same basis. The coefficients must be the same. Okay, a little proof concerning eigenvalues and eigenvectors for symmetric matrices. We're going to look at symmetric matrices for a little bit. I think through the remainder of the chapter, we'll see a good deal of symmetric matrices. Phase a symmetric matrix where CV is an eigenpair for matrix A, that is, V is an eigenvector, C a corresponding eigenvalue. With V transpose V, that is the norm squared of V equal to 1, so we've normalized that eigenvector. Then for any natural number K, we have A minus C times VV transpose to the K power equals A to the K minus C to the K times VV transpose. All right, we'll make a little comment here in a second that can be somewhat generalized. Let's go through a proof of that. All right, give a proof by induction. When K equals 1, it's an identity. When K equals 1, we simply have A minus C VV transpose. Over here, we simply have A minus C VV transpose. So it certainly holds when K equals 1. Suppose it holds when suppose it holds for K minus 1. We'll show it also holds for K. So there's our inductive hypothesis. Suppose I replace K with K minus 1 and we get an equality. Then what happens for that quantity raised to the K power? Well, that quantity raised to the K power is that quantity raised to the K minus 1 power times another copy of that quantity. Well, we, by the induction hypothesis, said when we take this quantity and raise it to the K minus 1 power, we get this stuff on the right-hand side. So we can replace the K minus 1 power with this stuff. All right, there's the induction hypothesis. Here's the extra copy. Now we'll follow our nose on the algebra. FOIL, I'm going to take the product here, FOIL it out, use the distribution properties and associativity properties if needed of matrix multiplication, and that will produce this. All right, so now we want to simplify it down. All right, here we've got matrix A, actually a power of matrix A applied to matrix B. So I want to concentrate on this A to the K minus 1 times vector V. Hey, A to the K minus 1 times vector V, I could treat that as A to the K minus 2 times AV. But wait, A times vector V is the same as C times vector V. CV is an eigenpair. So I could replace one of the copies of A with the scalar C as a multiple. And I can do that K minus 1 times and ultimately conclude that A to the K minus 1 times vector V is the same as C to the K minus 1 times vector V. So we can take this A to the K minus 1 vector V, replace it with a scalar multiple C, K minus 1 times. Here's another copy of C. Let's multiply out there. That'll give us C to the K, VV transpose, negative. Hey, here's a positive C to the K, VV transpose out here, so we can simplify by eliminating those. All right, so that just leaves this part here. V transpose A. Let's use our little trick of a product of transpose of a product and rewrite that as A transpose V transpose, reverse the order and insert transposes. Okay. Hey, A transpose equals A, right? Right. Hypotheses were that A was a symmetric matrix. So we can replace the A transpose simply with A and get something of this sort. Again, A times V, since V is an eigenvector, is the same as C times V. So we replace AV with CV. There's a transpose to be processed as well. Transpose goes on the vector. The scalar can be brought out. Let's bring it out over here. And then we get A to the K minus C to the K VV transpose. And that's exactly what we were supposed to get. So the result holds for K, assuming it holds for K minus 1, and mathematical induction tells us this result holds for all K. This could be generalized as follows. Okay, here we had symmetric matrix, eigenvector, eigenvalue. One of the exercises is stated as one of the exercises related to this previous result is the following. Take A to be a square matrix, but not necessarily symmetric. Let W be a left eigenvector for eigenvalue C, and let V be a right eigenvector for eigenvalue C, where W transpose times V equals 1. So it's the same kind of normalizing deal that we had in the previous. And it's almost the same conclusion. We'll take A minus C VW transpose to the K equals A to the K minus C to the K VW transpose. Okay, if we had the symmetric matrix, we'd have left and right eigenvectors the same, and we could then replace the W down here maybe with a V under those hypotheses. So you see that this result is a special case of this. Replace W transpose with V transpose, and we would get exactly that. So a slight generalization using those one-sided eigenvectors. Next, a useful result. So a large catalog of results, but this one we're going to use several times in the remainder of this section. It says any real symmetric matrix is positive definite if and only if its eigenvalues are positive. All right, we define positive definite in terms of the behavior of quadratic forms. Remember the X transpose AX quantities. We require those to be positive for all vectors X except for the zero vector. Well, it turns out that positive definite stuff relates to the positiveness of the eigenvalues for real symmetric matrices. And we can replace positive with non-negative and make a similar statement in the second claim. Let's look at proof of that. Okay, so claim is real symmetric matrix is positive definite if and only if all the eigenvalues are positive. All right, theorem 3.8.a said A, being symmetric, is orthogonally diagonalizable. So we saw that all symmetric matrices are orthogonally diagonalizable. So we can write A as V, C, V inverse, where V is orthogonal. So V, C, V transpose, V inverse and V transpose are the same thing for orthogonal matrices. That was theorem 3.7.1. It's the first property we had of orthogonal matrices. So if we take any vector X in Rn, okay, we're going to address positive definiteness. So at some point we've got to introduce an arbitrary vector. Probably going to want to make it non-zero pretty soon to deal with positive definiteness. But first a computation. Any vector X, we take X transpose AX. That's the same as X transpose. Replace the A with VC V transpose. Okay, times X. Let's associate the left two and the right two quantities with the C stuck in the middle. With the same, we've got roughly the same thing outside. One is a transpose of the other. So let's introduce a new variable, y equals v transpose x. Okay, so that'll give us a y on the right-hand side, and then y transpose will equal this quantity. So we can rewrite this x transpose ax as a y transpose cy. So if x is non-zero, then y will be non-zero, if and only if non-zero. So x is non-zero if and only if y is non-zero. That's related to the fact that V transpose is invertible. It's an invertible matrix. It's a full rank matrix. There's probably 3 or 4 ways we could explain it. But we get x is 0 if and only if y is 0. So we have x transpose ax being greater than 0 if and only if y transpose cy is greater than 0, where y is defined like this. That is, this is the condition of positive definiteness. That is, A is positive definite if and only if y transpose cy is greater than 0 for non-zero y. All right. Denote the entries of vector y as y sub I. And what happens with y transpose cy? Remember, C is a diagonal matrix, and that's what we got into up here with the orthogonally diagonalizable property of matrix A. So C is a diagonal matrix. Okay, so what happens when you take y transpose, that'd be a row vector, and multiply it by matrix C? You'll do your row times column thing. What will happen is the entries in this row vector, y transpose, will largely hit zeros when we go down the column of matrix C until we reach the diagonal. When we reach the diagonal in C, we will be at entry y sub I, say, y sub I of matrix Y, where we hit C sub I, or the C sub I entry of vector C. So we're treating the C sub I's as, excuse me, as the diagonal entries, as we created diagonal matrices before. In fact, they're eigenvalues. We know from the way we created the orthogonal diagonalizable matrices. But what we'll get then is a y sub I times c sub I, say, from this product. Multiply that by the column vector y, and you'll pick up another y sub I. Just the way you multiply row vector times square matrix times column vector, it'll produce these things here, largely based on the fact that C is a diagonal matrix, lots of zeros. Okay, so here's what we get out of that. Notice this is a quadratic form itself. So if each of the C sub I are greater than 0, then this summation will have to be greater than 0 because not all of the y sub i's are 0. Right? We said x is non-zero, and that's equivalent to a claim about y being non-zero. So when we take a non-zero vector y, we know that some of the components are non-zero. And so this summation will be non-zero. And so this y transpose cy will be greater than 0. This quadratic form here will be greater than 0. But I know that's equal to an x transpose ax quadratic form as well. And so we'll get that this x transpose A is greater than 0 from this property here. That is, A is positive definite. So if the C sub i's are positive, then A is positive definite. So yeah, oops, let's see, I'm looking to glue this together. We're going 2 ways on the logic. So we've shown, see, the C's would be the eigenvalues. To glue it back together with this, we've shown if the eigenvalues are positive, there we go. So if each of the C sub i's are positive, then this quadratic form will be positive, and this quadratic form will be positive, and A will be positive definite. So the C sub i's, because we got them through the orthogonally diagonalizable properties, the diagonal entries of C, where the eigenvalues of matrix A. If those eigenvalues are positive, we're getting positive here, here, and positive definite. So that shows if eigenvalues are positive, then matrix is positive definite. Okay. Next, we want to show if positive definite, then eigenvalues are positive. Okay. This Y we had in the previous computation in the Y transpose, here it is Y transpose CY, could be any vector, any non-zero vector. And we knew we would get out something that's positive. So let's choose Y as the ith standard basis vector for Rn. So a bunch of zeros and a 1 in the ith position. All right, let me go back. Here's what we were getting for that Y transpose CY. Well, if I choose the components of vector Y, the Y sub i's here, to be 0, 0, 0, 0, 1, 0, 0, 0, 0, you're going to lose all but one of these. And you're going to be left simply with, if I made the ith one of the Y sub i's, it's a little redundant there. But if I make one of these 1, you pick off a single eigenvalue. So by choosing Y to be the ith standard basis vector, when we go through and do this computation, you'll be left with a single eigenvalue, the ith eigenvalue, using the ith standard basis vector. Okay, so if we make an assumption that A is positive definite, that's equivalent to making an assumption that this thing is greater than 0. Well, this thing equals C sub I, so that implies C sub I is greater than 0. We could have used any standard basis vector up here from the first to the nth one, picked off any of the eigenvalues, and be led to the conclusion that A is positive definite implies eigenvalue is greater than 0. Do that for each of the i's, you get all of the eigenvalues are greater than 0. So if positive definite matrix, then positive eigenvalues. Non-negative definite, it's all the same thing, just change the greater than, the strictly greater than's to greater than or equal to's and follow the same argument. So, useful stuff. Real symmetric matrix is positive definite if and only if its eigenvalues are positive. So I can relate positive definiteness, that thing about quadratic forms, I can relate that to signs of eigenvalues. Maybe didn't see that coming. If a square matrix A is positive definite and orthogonally diagonalizable, that is if we can write A in this form here, where V is orthogonal, A inverse, that'd be the inverse of VC, V transpose. Okay, that would be, reverse the order on these, that'd be, let's see, VC inverse, V inverse. So I'm a little puzzled by what happened here. We got an inverse transpose. Let's see, an inverse over here. Oh, excuse me, mildly confused. Let's see. V transpose is V inverse, orthogonal matrices. All right, so we should have a V inverse inverse over here on the left, and we do. We should have a C inverse in the middle, and we should have a V inverse on the right. Yeah, so this is correct. Excuse me for a second. Yeah, V transpose and V inverse are the same. V is an orthogonal matrix. So we get an expression of this form, and there we go again. Yeah, V inverse is the same as V transpose. So we can take A inverse and write it in terms of this. Notice it involves V's and V inverses. By the way, you can find C inverse easily. Yeah, I think so. Being a positive definite matrix, the eigenvalues are all positive, as we just saw. The eigenvalues will be the diagonal entries of matrix C. So the diagonal entries of C inverse, it'll be the reciprocals of all those eigenvalues. They'll still be positive. No worries about division by 0 because we're dealing with a positive definite matrix. That's why that's the context. But we see then that the C inverse also is positive definite. So we get this relationship between A inverse and a positive definite matrix, applying theorem 3.8.14, relating it to the eigenvalues. Okay, another result, the first part of which I'm mildly interested in, the second part of which, let's read that before we get into the proof, as there's some motivation for the second part, and the second part's based on the first part. Part one, if symmetric matrix A is positive definite, then there's a non-singular matrix P such that P transpose AP equals the identity. All right. If symmetric matrix A is non-negative definite and A equals V, C, V transpose, where V is orthogonal, we know such a thing exists for symmetric matrix, and C is diagonal matrix with the entries C1 through C sub n, where those are the eigenvalues of matrix A. Then there's a diagonal non-negative definite matrix S such that VS V transpose squared equals A. We found a matrix such that when we square it, we get matrix A. Now we had some conditions on matrix A. It had to be symmetric and non-negative definite. But this will allow us to define a square root of a matrix A, satisfying those certain conditions. The next little definition is if symmetric matrix A is non-negative definite, the hypotheses we just had, then this matrix VS V transpose we were just talking about, where I square VS V transpose to get matrix A, is called the square root of matrix A, denoted A to the 1/2. I've had some problems with this kind of thing in the past. I'm okay with this. I'm okay since we've cleanly defined the square root of a matrix. I'm okay with using those symbols. But that's the plan for this matrix. So let's go through proof. First part, I'm not terribly enamored with. Second part I am, because it allows us to talk about square roots, and it uses the first part. Okay. So let's take care of this part. Symmetric matrix A, positive definite. We're looking for a non-singular and invertible matrix P such that P transpose AP equals the identity. All right. We know we can write A as V, C, V transpose for an orthogonal matrix V, and where C is a diagonal matrix with the eigenvalues of matrix A in it. That theorem simply established the existence of that kind of factoring of matrix A, factorization, provided matrix A was symmetric, which is our hypothesis. All right, A is positive definite. Well, we just saw that means all of these eigenvalues are positive. So we can define a matrix S as a diagonal matrix whose diagonal entries are the square roots of the eigenvalues up here. Knowing they're positive tells me I can take square roots and have no concerns about complex numbers. So we're good on taking square roots of those positive real numbers and defining a matrix S. Hey, if you square this matrix S, piece of cake to square a diagonal matrix, you square the diagonal entries. And of course, when I square the diagonal entries here, I get the diagonal entries there and all the zeros off the diagonal. So indeed, S squared equals matrix C. So if we take matrix A, which we've written as A, C, V transpose, replace C with S squared, that'll give us V, S squared, V transpose. You can write that as VS times S, V transpose. We could transpose this S matrix. Remember, it's a diagonal matrix, symmetric, so transposing it doesn't do anything. That's why equality. We could group those first two together, group the second two together, S transpose, V transpose, write that product of transposes as a transpose of the product, V times S. So here we've written A as VS times VS transpose. All right, V is orthogonal. The ith column of V times S is the square root of C sub I times the ith column of V. Let's make sense out of that. All right, so if I take this matrix V and multiply it on the right by a vector, remember, I get a linear combination of the columns of vector V with the entries, the components of that column vector as coefficients. Okay, well, when I take vector V times vector S, I get that for the first column and for the second column and for the third column and for the ith column. So what happens when I multiply vector V times the ith column of vector S? Well, the ith column of vector S reads 0, 0, 0, 0, square root of C sub I, 0, 0, 0, 0. So we get a linear combination of the columns of matrix V with coefficients 0, 0, 0, 0, square root of C sub I, 0, 0, 0. And the square root of C sub I will be multiplied by the ith column of vector V. So that's why in that matrix product, the ith column is the square root of C sub I times the ith column of matrix V. So the columns of V times S are linearly independent. Yeah, that's because we've got the columns of VS simply as scalar multiples of the columns of V. And those scalars are these square root things. Those are all non-zero, right? So we didn't lose anything in terms of a rank. But right, we had positive eigenvalues, so these square roots are also positive. So the columns of VS are linearly independent. All you've done is take a linearly independent set of vectors and scaled them by a positive constant, each of them individually. That keeps them linearly independent. So if the columns of VS are linearly independent, then VS is a full rank, and being full rank, it's invertible. So we can talk about VS inverse. All right, so let's see. The important observation we're going to need on the next slide is A equals VS times VS transpose. All right, consider VS inverse times A times VS transpose inverse. Remember, I just said we could write A as VS times VS transpose. And here we've multiplied by a VS inverse on the left and a VS transpose on the right. So were we to do this, we get the identity out. Or if we can show this equals the identity, then we're good. So VS inverse times A times VS transpose inverse. All right, let's see. Transpose inverse is the same as inverse transpose. Theorem 3.3.7 told us that relationship between inverses and transposes and swapping the orders there. So we can do that kind of swapping. Now we've got a matrix and its transpose. I want to let P be this matrix. So when I transpose this matrix, including the transpose, let P equal VS inverse transpose. If I transpose that, I get the VS inverse. So we've got P transpose A P when we define that to be P. And that's what we were looking for. And oh yeah, we had A as V times S times V times S transpose. And we'd get cancellation on the left with this and on the right with this, and we get an identity out of that. So the identity equals P transpose AP, and this is the P we're choosing. Okay, that's cool, but it's this thing here that we're interested in because we'll use this to define square roots and motivate a conversation about Rth roots, I think we'll do. Okay, in part one, so we're going to recycle some of that. We took S to be the diagonal matrix with the square root of the eigenvalues along that diagonal. All those entries along the diagonal are non-negative. So S is non-negative definite by 3.8.14. Okay, down here, we've got a hypothesis of non-negative definite. Up here we had positive definite. So we just lose the not equal to zero part of the argument we had above. So we might have zeros for eigenvalues, and the square roots, some of these might be 0. So we'll have that S then is non-negative definite because we get these eigenvalues C1 through C sub n as, these eigenvalues, these diagonal entries, square root of C1 through square root of C sub n. Get these as non-negative. So S itself is non-negative, as we argued above. In a diagonal matrix, the eigenvalues are the diagonal entries. And these are the diagonal entries for S. We had S squared equals C, okay, because we're dealing with diagonal matrices. I love diagonal matrices. So remember V inverse equals V transpose. V is orthogonal. With A equals VC V transpose. Okay, A equals VC V transpose. We know we can do that. Theorem 3.8.A told us you can do that for symmetric matrix, and you got a symmetric matrix. So A can be written like this. We've got C equals to S squared. I can split the S up and stick an identity there in the middle. Hey, let's write that identity as V transpose times V. Hey, V transpose times V, V transpose is V inverse, no problem. That's VSV transpose times VSV transpose, that's VSV transpose squared, and it equals matrix A. So the second part went really smooth once we had the first part. So there's a way to find, for a symmetric, non-negative definite matrix, a matrix, VSV transpose, such that when we square that matrix, we get the matrix A back. Allowing us to define, back to the notes, the square root of a matrix, as we observed. We could define similarly, kind of wish they hadn't used R, because I think of that as rank, but R is a natural number. We could define the rth root of A simply by setting the diagonal matrix S equal to the rth roots of those eigenvalues. If A is symmetric and positive definite, all those eigenvalues are positive. Yeah, that's what we just showed in Theorem 14. The determinant of A is the product of the eigenvalues. We showed that in passing. I guess it was a section. The section's so long. Yeah, the determinant of a matrix was the product of the eigenvalues, and the trace was related to the sum of the eigenvalues, wasn't it? I think that's what that theorem said. So if we got positive eigenvalues, then we see that this matrix A has a positive determinant, and so is invertible. We related inverses to determinants in, I guess, that theorem. C is an eigenvalue of A, and 1 over C is an eigenvalue of A inverse. We said that somewhere along the lines. It's a straightforward computation to show. So, hey, if A is positive definite, then A inverse is positive definite as well. So we can define a square root of A inverse because we can define square roots of symmetric positive definite matrices. And we could denote that, say, as A to the negative 1/2, and we could similar find A to the negative 1 over R matrices. What we could do with repeated multiplication now is make sense out of A to any rational power, provided A is of sufficient form, symmetric and positive definite, say. Then we could go through and deal with raising A to any rational power, taking the root part from this and then just repeated multiplication in terms of the numerator of that rational power. Okay, here's a little comment in passing about a generalized eigenvalue and generalized eigenvector. I don't think we'll use this. I don't think we'll use it at all. But, it's in the book. Let's get it out on the table. Suppose A and B are square matrices, n by n. A value C such that the determinant of A minus CB equals 0 is a generalized eigenvalue of A with respect to matrix B. Hey, if matrix B is the identity, then it's a regular old eigenvalue. If V is in Rn, satisfies AV equals C times BV, then V is a generalized eigenvector of A with respect to B for generalized eigenvalue C. Again, if we take B equal to the identity, it's the old stuff. But there's some more general ideas of eigenvalues and eigenvectors than the ones we deal with. And we're not going to really deal with them, I don't think, in here. There may be a homework exercise related to some of that. All right, general claims without proof that every n by m matrix has a, to be defined, singular value decomposition. Let me give you the definition of that, and let's go to a different source, and we'll establish the fact that every matrix has a singular value decomposition. All right, here's what we mean by that. You hear decomposition, you ought to be thinking writing the matrix as a product. Factorization is how we've dealt with it before. For n by m matrix A, a factorization of the form A equals U D V transpose, where U is an n by n orthogonal matrix, V is an m by m orthogonal matrix, and D is an n by m diagonal matrix with non-negative entries, is a singular value decomposition of A. All right. I want to say something about matrix D. It's claimed to be a diagonal matrix. Remember, we defined diagonal matrices even when a matrix wasn't square. We defined the diagonal of a matrix even when it wasn't square. So what we've got then for matrix D is an n by m matrix. If n and m are different, there's either a row of zeros or a column of zeros. It depends on which one is larger. An n by m diagonal matrix has a minimum of m and n elements on the diagonal, and all the other entries are zero. So it might be a little unusual to you, it is to me, to talk about non-square diagonal matrices, but that's what it means. The non-zero entries, those entries along the diagonal of D, which are non-zero, are these singular values of A. So we want to take A and write it in this form. It's kind of a type of diagonalization of matrix A, kind of an orthogonal diagonalization. I mean, we're using orthogonal matrices. We're not using the, V and a V transpose. We're using a U and a V transpose. So it's a little more general. If A is square and symmetric, I think we're probably back where we were before with regular old orthogonal diagonalizability. The following proof is from Harville's book and says, no constraints on matrix A, just let it be n by m. There exists a singular value decomposition of matrix A. All right, so sort of a big claim. Let's go through a proof, not in Gentle, a proof from Harville. Okay. All right, let's see. We might have to run back and look at some of these referenced results as well in the notes. So first, A transpose A, look at the dimensions. That's an m by m matrix. Of course, it's a symmetric matrix. It's a non-negative definite matrix by Theorem 3.3.14 part 2. Okay. A transpose A is non-negative definite. Let's go look that up. Section 3.3. Let me bounce back to my notes. If I got my wits about me, I got 3.3 here. Here's 3.3.14, and there's part 2. We took here a n by m matrix. Part 2 says matrix transpose times matrix is non-negative definite. Okay, so that's exactly what we had. Non-negative definite. Okay, by Theorem 3.8.14, we just did that one. For a non-negative definite matrix, the eigenvalues are non-negative. For positive definite matrix, the eigenvalues are positive. That's that thing we just did, relating positive definite and non-negative definite to the positiveness and non-negativeness, respectively, of the eigenvalues. So A transpose A has eigenvalues that are non-negative. All right. We've done this so many times, I don't feel, let's maybe make it bigger. Theorem 3.8.a says, take this symmetric matrix, it's orthogonally diagonalizable. that we've done a bunch of. It's just a claim that a symmetric matrix is orthogonally diagonalizable. So there exists, let's see, A transpose A, that's M by M. So these orthogonal matrices in this conversation will be M by M. There's M by M orthogonal matrix Q, such that the given matrix, A transpose A, not just A itself, is Q, C, Q transpose, where C has along its diagonal the eigenvalues of the matrix we're talking about. We're not talking about matrix A, we're talking about symmetric matrix A transpose A. Okay? That's how we diagonalized matrices before. Okay? Let R be the rank of A. We know the rank of A transpose A is the same as the rank of A. That was Theorem 3.3.14, part 6. Just to ease your restless mind, let's check on that one. So that's where we just were. Part 6 says, yeah, the rank of A transpose A equals the rank of A. All right. So the rank of A transpose A equals the rank of A, and we've just denoted it with an R. By Theorem 3.8.12, R is the number of non-zero eigenvalues of A transpose A. Okay, let's look at that again. I guess we did that recently as well. 3.8.12, 3.8.12, I had these hiding in the background, said the number of non-zero eigenvalues of a matrix is equal to the rank of that matrix. Okay, and that's exactly what we had, except here we had the matrix A transpose A instead of the matrix A. But the rank of that matrix is R, so the number of non-zero eigenvalues of that matrix is R. Define an R by R diagonal matrix of rank R as given here. So we're taking the D1 to be a diagonal matrix whose entries are square root of the first, square root of the second, up to square root of the rth. Up here, we have indexed these eigenvalues in such a way that they are in decreasing size. We know they're non-negative by comment above. So lay them out in decreasing size. That means if there's any zeros, they're going to occur at the end. We've got our non-zero entries, so it must be C1 through C sub R. After that are the zeros, if present. So define D1 to be the diagonal matrix with these square roots along the diagonal. Okay, it's an R by R matrix. We're going for, let's keep an eye on the prize here, a singular value decomposition of A. So we're trying to write A as a product of two orthogonal matrices on the outside with a diagonal matrix on the inside. This won't do, it's not the right size, but we're on our way. Okay, so D1 is diagonal, there's the entries. D1 is a full rank, I mean, it's an R by R matrix, and it's certainly full rank. So D inverse exists. All right, take our partition matrix Q. Okay, we had introduced matrix Q. Let's look back at that. Here, it came up in the orthogonally diagonalizability of the symmetric matrix A transpose A. So we're taking this matrix Q right here. We're going to break it into Q1 and Q2, partition it into Q1, Q2, where Q1 is M by R, and Q2 is as appropriate, M by N minus R. I think the N minus R parameter pops up there. Q was M by M, if memory serves. Define N by R matrix P1 as follows. Matrix A, matrix Q, and that D1 matrix that we just introduced. Dig your way through the dimensions. That will produce an N by R matrix P1. Let P2 be any, okay, so I may be losing uniqueness right here, but there's more to follow. Define P2 to be any N by N minus R matrix such that P1 transpose times P2 equals 0. P1 being given by this up here. It's just computational. and we're headed in a direction. But it's going to take a little while to get there. All right, is there any such P2 that satisfies this? Well, yeah, we could take P2 to be the appropriately sized matrix of all zeros, and it would satisfy that. But we're saying if we take any matrix P sub 2 that satisfies this little equation right here, that's how P sub 2 is being chosen. It could be all zeros. So there exists such a matrix P2. We're going to put some added conditions on it here on down the road related to some null space stuff. But what we're about to use is nothing other than this equation here. So pick a P2 that satisfies this. All right, create a matrix now. Matrix P, be an n by n matrix. If you look at the dimensions, P1, the partition matrix, P1, P2. P2, I really know only this about. P1, I've got an equation for P1. All right. We, on the previous page, had this symmetric matrix written because it is orthogonally diagonalizable as QC, Q transpose. This little equation implies, remember the Q's are orthogonal matrices, so they're inverses or they're transposes. So we can take this Q to the other side on the left and write its inverse, which is its transpose. Take this Q transpose, which is really Q inverse, take it to the other side as a Q. So move the Q's to the left-hand side, we get Q transpose, AQ. We get the C left only on the right-hand side. And we know matrix C can be written like this. Remember the D1 squareds? Well, remember the D1? That was the square roots of the eigenvalues of matrix A. That was the square roots of the positive eigenvalues of matrix A. So when I take D1 squared, it gives the positive eigenvalues of matrix A. And it was a possibility that there were some eigenvalues of 0. 0 can be an eigenvalue, 0 vector can't be an eigenvector. So what we've got is non-zero eigenvalues of matrix A, followed by 0 eigenvalues of matrix A. So certainly C equals that. Okay, now we had partitioned this Q matrix up. Here it is. Q is partitioned like this, so Q transpose will give us this kind of row partitioning as a column partitioning with transposes thrown in. That's how you transpose a partition matrix. A transpose AQ. All right. We'll do our row times column stuff and all this multiplying, and it'll produce this partition matrix. Trust me. See, I got a 1, 1, a 1, 2, a 2, 1, and a 2, 2. So those sound reasonable. That's how the Q1 and Q2 with transposes on these have been distributed throughout there. There's an A transpose A in the middle of all of them, as there's a A transpose A in the middle of this product. I can't move the order around, of course, we don't have commutativity. Trace through the dimensions, you'll find that what we've got here, Q1 transpose, A transpose A, Q1, this is R by R. All right, hey, this was R by R as well. All right, so we've got Q transpose, A transpose, AQ written in two different ways. This way and this way. Q transpose, A transpose, AQ. So we've gotten this matrix written in these two different ways, where the dimensions are the same in this upper left-hand corner. So the dimensions are the same throughout, but we're interested in the upper left-hand corner. Given it's the same matrix, we can draw the conclusion, given the dimensions, that Q1 transpose, AQ1, this thing here equals D1 squared. All right. Also, let's see, down here, this is, what are the dimensions on this? I think we're dealing with, is this M minus R by M minus R? I think we're dealing with down here. Anyhow, what we've got down here is, must be the zero matrix. Dimensions are the same in the upper left-hand side. All the dimensions are the same. I can draw conclusions about these two entries as well. Not going to do it. I'm going to draw a conclusion about this entry, Q transpose, A transpose, A, Q transpose, right, equals, let's take this product of transposes and do our little thing with that, but it must equal 0. It's that 0 there, appropriately sized 0 matrix. Looking at this second equation, we've got a matrix on the right times its transpose on the left equal to 0. That implies that matrix on the right is 0. Theorem 3.3.14 part 1, let's look it up. So we've got a matrix times its transpose. Matrix on the left, transpose, sorry, matrix on the right, transpose on the left. 3.3.14, 3.3.14, matrix times its transpose. Oh, here it is, part 1. A matrix times its transpose with the transpose on the left implies the matrix must be 0. A transpose A equals 0 if and only if A equals 0. Yeah, that's what we had. Except the matrix we had here is AQ2. So we got AQ2 transpose times AQ2 equals 0. That result we just looked at implies AQ2 equals 0. P1, we define P1 up here as AQ D1 inverse. So if we transpose P1, we'll transpose this product. Okay, we'll take D1 inverse and transpose it, D1 inverse. That's a diagonal matrix. So it's symmetric. So I don't draw the transpose symbol. It's symmetric, it equals its transpose. We get a Q1 transpose in the middle, and we get an A transpose on the right. So let's see, we'll multiply both sides by D1. We'll lose the D1 inverse on this side, pick up a D1 on that side, and get Q1 transpose A transpose equals D1 P1 transpose. Multiply both sides by D1 and wrote it in the opposite order. If you like, I can transpose both of those. I want to for reasons to be made apparent later. Transpose this product and you get AQ1. Transpose this product and you get P1 D1 transpose, which is the same as D1 because D1 is a diagonal matrix. All right, there's a bunch of relationships. It's a computational argument. We're going to need lots of these identities on the next slide. So I'm going to bounce back and forth, and we'll come back and make sure when I make a claim on the next page, it's justified by some of this stuff. Definition of P1, some relationships between A and Q2 and A and Q1, D1 squared, we've got written in a certain way. Let's see what happens. All right, so P transpose AQ. We had P, we wrote it as P1, P2 as a partitioned row matrix. Transpose it, gives us this. A, Q was defined in terms of this partitioning. Do your row times column stuff, similar to what we had on the previous slide, and it produces this. And start using information you know. All right, P1 transpose. I know what that is. That's D1 inverse, Q1 transpose, A transpose. P1 transpose, let's go to the previous slide. P1 transpose. There it is right there. D1 inverse, Q1 transpose, A transpose. Back to our original location. AQ1 is P1 D1, AQ2 is 0. Let's go back. AQ1 is P1 D1, AQ2 is 0. Okay, so we're taking the P1 transpose, replacing it with this stuff. Here's an AQ2 in both of these spots. We can replace those with zeros. The replacements are in parentheses. Here's an AQ1 here in the 2-2 position in the partitioning. AQ1 equals P1 D1. So I'll replace this AQ1 with P1 D1. Yeah, I see an AQ1 up there as well, but we've done a different substitution so far. All right. So in parentheses, we've got the substitutions. Let's simplify a little bit. Get zeros here on this right-hand part. let's see, we can associate P2 transpose and P1 and transpose that product. We got our reasons for doing that. So P1 transpose P2 transposed would give us P2 transpose times P1 transpose times P1 would give this. So we got the books balanced in that location. All right. Here, let's see, we had D1 squared as this product with the Q1s on the outside and the transpose on the inside. There it is right there. This stuff here was D1 squared. Whoops. Let's go back and find that. D1 squared in terms of Q1s and A's. D1 squared in terms of Q1s and A's. So we'd established all of that. Make that substitution for this part here. Then we're left with a D1 inverse, a D1 squared. From that substitution, we played around with the transposes there. Hey, D1 inverse times D1 squared is just D1. We got zeros over here. And didn't we show P1 transpose P2 equals 0? We did. That was the requirement on P2. So let's go find that one. P1 transpose P2. There it is there. P2 was any matrix of the appropriate dimension such that P1 transpose P2 equals 0. We needed that condition. We could have used a 0 matrix, but P2 can be any matrix that satisfies that condition. We didn't use that condition until we got to here. All right. Is that a diagonal matrix? It is. It's got some zeros along that diagonal, but it's a diagonal matrix. All right. So we're going for singular value decomposition. We're closer than ever. Need to move some matrices around. Let's see. P transpose AQ is N by M, if I trace through the dimensions. P1 transpose P1. We had P1 transpose. Let's see. Here it is right here, defined as this. So here's the P1 transpose. Transpose that to get P1 itself. So that'll produce this. As given above, let's see, that equals, whoops, that equals, let's just drop the parentheses. That's all we've done from here to here. No, deal with the transpose of the products. Let's see, D1 inverse transpose is just D1 inverse, it's diagonal. Then we'll have a Q1 and preceded by an A. So there's the A, Q1, D1 inverse from transposing here. All right. We had this relationship with D1 squared. There it is. And I got it right here. We looked it up just a second ago from the previous slide. So we can take this Q1 transpose A Q1, these center 4 matrices, and replace them with D1 squared. Now we got D1 inverse, D1 squared, D1 inverse. That's an identity matrix. It's an R by R identity matrix, but we're getting close. Okay. So we just took P1 transpose times P1 and showed we got an identity matrix. That means P1 inverse is P1 transpose. Theorem 3.7.1 tells us, that means P1's an orthogonal matrix. Matrix is orthogonal if and only if its inverse is its transpose. Okay, so P1 is orthogonal. Now we need to talk, and we're almost there, we need to talk null spaces. The dimension of the null space of this matrix is n, it's an n by n matrix, minus the rank of this matrix. Okay, P1 was n by n. It had n columns, is what matters. But P1 transpose, null space, number of columns minus the rank. This is the rank nullity equation. Let me see if I've got that at my fingertips from section 3.5. I do not have section 3.5 pulled up, so let me not waste time fishing for it. Back to where we were, there you are. But this is the rank nullity equation. Nullity equals number of columns minus rank, or better yet, rank plus nullity equals the number of columns. This is the rank nullity equation. Applied to the matrix P sub 1 transpose. Okay, We saw earlier that the rank of A transpose A equals the rank of A. So we've applied that to the matrix P1. So the rank of this product is the same as the rank of P1. The rank of a matrix equals the rank of its transpose. It was an early on result about ranks. So the rank of P1 transpose, I'm looking for this number here. Rank of P1 transpose is the same as the rank of P1 transpose times P. The rank of P1 transpose times P is the same as the rank of P1. P1 transpose P multiplied together to give us the identity on the previous slide. So this is a substitution. That product equals the identity. An R by R identity matrix has rank R. So the dimension of the null space of P1 transpose is N minus R, N minus R. All right, what we're working on is singular value decomposition. We're working on getting matrices of the appropriate dimensions. We've partitioned and looked at the parts, the P1s and the Q1s and so forth. We're trying to build it back together and get the singular value decomposition of matrix A. And that required some square matrices, which will be the P's and the Q's when we're done. All right, so the dimension of the null space, N minus R. Let P2 be any N by N minus R matrix whose columns form an orthonormal basis of the null space. Okay, well, now we put a condition on P sub 2 earlier. It was this. We needed P1 transpose times P sub 2 to equal 0. Can we let P sub 2 have as its columns an orthonormal basis for the null space of P1 transpose? What's going to happen? The columns of P2 will be orthonormal, and there'll be a basis for the null space of P1 transpose. What happens when I take one of the columns of P2 and multiply it on the left by P1 transpose? What does P1 transpose do to things in the null space of P1 transpose? Maps them to 0. So P1 transpose maps the first column of P2 to 0. P1 transpose maps the second column to P2 to 0. It maps all the columns of P2 to 0, so it maps the whole matrix to the 0 matrix. Why is that? Because the P sub 2's are elements of the null space. More than that, we've chosen to be orthonormal basis because we're going to need orthogonality here in a second. But we do have that equation satisfied for this choice of P sub 2. And that was the only condition on matrix P sub 2. So we can choose P sub 2 as such. You'll get this property that we needed as required above. P sub 2 times P sub 2 transpose. That'll be an identity of size N minus R. Why is that? We just made P sub 2 orthogonal by making its columns orthonormal. So we chose it to be an orthogonal matrix. There's your quote on that. Theorem 3.7.1, that thing we've used so many times. P2 transpose is P2 inverse. That's what that claims. So if we take P transpose times P, we're getting the big matrices out now. We had P expressed as this partition matrix. So P transpose will be this partition matrix. Do the multiplication the way you multiply partition matrices, and we'll get this. P1 transpose P1, that was an R by R identity matrix. It's the last computation on the previous slide. P2 transpose times P2 is an N minus R by N minus R identity matrix. So that's an identity matrix. That is, P transpose times P is the appropriate sized identity matrix. So P is orthogonal. That is, P transpose equals P inverse, that theorem again. All right, upstairs, we had P transpose AQ, I started as an equation, was equal to this diagonal matrix. Let's just call it D for diagonal matrix. Okay, it's got some zeros on the diagonal, but that's cool. It's still a diagonal matrix. So in other words, if we'll take the P and the Q to the right-hand side of this equation, P transpose, which is really P inverse because it's an orthogonal matrix, as we just showed. So this goes to the other side as a P itself. The Q goes to the other side as a Q inverse, but Q is orthogonal, as mentioned upstairs. So we get a Q transpose on the right. Q is orthogonal from the first few lines of the proof. So we get A equals P, diagonal matrix, Q transpose. P is an n by n orthogonal matrix. Q is an m by m orthogonal matrix. Let the U and the V in the statement of the theorems be P and Q respectively. And there's your single value decomposition. Is it unique? Oh, no way. Hey, up here, when we chose P sub 2, we took its columns to be an orthonormal basis of the null space. Is there more than one way to do that? Yeah, if it's more than dimension 1, at least there is. I could take those columns in a different order, and P2 would still satisfy all the conditions we need, and it would be different and would cascade down through this, causing some sort of differences, I guess, in matrix P, I think. But I don't see anything in this that it would tell us that we get uniqueness in these singular value decompositions. To the notes. All right, so big result there. I think we've only got one more result to look at in this section, one more proof. Another definition, let A be an n by m matrix of rank R with singular value decomposition, like we had just defined. A equals U D V transpose. D is a diagonal matrix, let that be its entries. Here, as above, D is n by m, it's the same dimensions of matrix A. And take the eigenvalues, or the diagonal entries, I guess I should say, to be D1 greater than D2 up through D sub n, so we'll take the 0 ones last. Let the columns of U be U sub I, let the columns of B be V sub I. Then we can express A in terms of this particular singular value decomposition as a sum from I equals 1 to R, D sub I, and then this outer product of U sub I, V sub I transpose. This is called a spectral decomposition of A. So A can be written as this linear combination as well. This is related to the stuff we had upstairs. We've liberated ourselves a little bit upstairs. I think we probably had a symmetric matrix here. Here, not symmetric. Upstairs, we had orthogonally diagonalizable. Down here, not, but sort of, right? That's what a singular value decomposition is. A sort of orthogonal diagonalization. Diagonal matrix, orthogonal matrix, orthogonal matrix. The dimensions aren't the same and they're not the same matrix. So I don't have a VV transpose type thing. I've got a U and a V transpose in the singular value decomposition. So one final thing related to these spectral decompositions and Fourier expansions. Let A be an n by n matrix with spectral decomposition as given. Then the claim is, looking at these matrices, the inner product of U sub I, V sub I transpose, and U sub J, V sub J transpose is 1 when I and J are the same, 0 when they're different. The D sub I's, as we saw above, when we deal with the Fourier expansions, we'll get the coefficients, the Fourier coefficients out in terms of projections. Let's go through proof of that. Maybe one observation. This is an outer product of two vectors. All right, so these are matrices, right? These are outer products and matrices, not inner products and scalars. So this is a matrix inner product we're dealing with here. Okay. All right, so computational, not very long. All right, for matrices A and B, we computed inner products of those matrices by summing inner products of the columns. So we need a column, say the kth column of, to establish this, U sub I, V sub I transpose. Think how you multiply this column matrix times this row matrix and that will give you these entries in the kth column. We did something similar to this a while ago. So we get this kth entry from v sub I, and the first and second through the nth entry using the subscripts again, superscripts, using superscripts to indicate the location of the entry in these vectors. So kth entry in v sub I, first entry in u sub I, second entry in u sub I, and so forth. Think of how you multiply matrices, and that's what you get for the kth column. I need that so I can talk about these inner products. All right, so we'll carry this over. Take the inner product. All right, these were the relevant matrices that we made the claim about. Here we're taking kind of I equal to j. This is u sub I, v sub I transpose, inner product with itself. Could write that, here are those components we had for those vectors. Write them as, as column vectors. I'll transpose them so they'll fit on the slide. And it's just a regular old dot product. Multiply first components together, second components, and so forth. They're the same. You get this squaring. Okay. Let's see. We've got a common v sub I super k entry here. V sub I super k, we're summing from k equals 1 to m. So we can express this like this. I'm running low on explanations here. Let's see, it's just an algebraic manipulation. The goal line's in sight. There we go. Let's take a v sub I super k squared and factor it out of this sum. All right, we're summing over k, then we can pull that sum over there, get it together with a v sub I super k. The u's have i's and numbers, no k's, so they can be brought outside of the summation. So there we go, and we get this kind of thing here. Hey, this is the sum of the components squared of u sub I, so that's the norm squared of u sub I. Same thing, this is the sum of the squares of the components of v sub I, so that's the norm squared of v sub I. Remember, u and v were unit vectors, so we've got unit vectors, they're each of norm 1, and so this inner product is 1. All right. Also, we had some orthogonality going on. If we'll take u sub I, v sub I transpose, and u sub j, v sub j transpose, where I and j are different, same setup, same computation, similar computation. We can factor, not quite as cleanly, but what comes out of this is an inner product right here. Remember, these aren't exponents, but components in those superscripts. So we've got u sub I first component times u sub j first component plus second components plus product of nth components. That's an inner product of u sub I and u sub j, and equals 0 if I and j are different, establishing this claim here. The fact that we actually get these coefficients to be given by these projections is also computational and left as an exercise. And that finishes the oh-so lengthy section 3.8 on eigenanalysis. Well, there's everything you wanted to know about eigenvalues and more. Next section deals with norms of matrices. And that's the bulk of the course when we get through section 3.9. There's another section in 3.9. Some stuff we'll try to get to in chapter 4 and definitely in chapter 5, time permitting. But have a nice day. Glad to be done with section 3.8. Bye-bye.